Hello and welcome. We continue with the features that we can use to improve the plots in MATLAB. So we'll spend the rest of this lesson expanding on plotting features. So the last time we looked at this, right, to create different plots with features in them. In this case, we have a dashed line connecting the different points in the plot, or different markers that we can use to identify the points along the plot. Things that we can do. Other things that we can do, we can have more control over the line properties if we want to adjust them by using the line properties identifiers, and adjusting or putting a value definition on those identifiers. And multiple properties can be adjusted on a single line in the same plot, but each line requires a separate plot statement. So if I have different plots and I want to make them look different, I have to have the statements on separate lines. Now, in this example, we have, just to show the features, we have make the line connecting the dots a little thicker, so it can be, better identified. And you notice that the line width here is 2, and you use circles for the markers, and also a marker that is larger than the default value. In this case, we use the value 10, and the default is actually 6. So that's another thing that we can do to improve on the plots. Now, one thing I want to mention is that this statement here in purple is not part of the code here. I added it later onto the PowerPoint just to explain how we're using the line width and the marker size. Okay, so again, the line width in this case makes the width of the line thicker than the default. We use the value of 2, and the marker is also bigger than the default, and we use the marker size of 10. Excuse me, let's see, so we're here. All right. And that's what I was referring to. You probably weren't seeing that in the previous slide. As you can see, the size of the line, the line width and the markers are greater than the normal default. And like I was saying before, I added this purple statement here on my own. It's not part of the code, just to help you understand what the code is actually doing. All right, some more features that you can use. We have used this before when plotting to create the plots. The axis, we know it defines the axis, and you can use this function to freeze the current settings of an axis that you have. You have multiple plots and you want them all to keep the same axis. And there's some other features here that we're going to be using as we go along. We have already used some of this, like the text and the legend, right? But it's just for your reference. And so if you use the whole command to add a second line to your graph, the scaling cannot change. So if you want to return the control of the scaling to MATLAB, you have to just simply re-execute the axis function. Okay. So as long as you have hold on the statements or the commands, then it's not going to change your axis. You have to really reset them again if you want to change that. So for example, here this axis statement fixes the plot axis from -2 to 3 on the x-axis and from 0 to 10 on the y-axis. And saying axis equal is going to scale the same on the X and Y axis. So it's not going to change. It's not going to keep this default values, but it's just going to make them equal, right? If you want to have something that looks, even or balanced, if you will. Also, to add a legend to a plot, we can use the legend function. It requires a legend in the form of a string for each line plotted. And the false to a display, if you remember, in the upper right hand corner of the plot. The text function will allow you to add a text box on your plot, which is useful for describing features. It requires you to specify the location where you want the text box included. And again, it's another feature that we can use to improve on the plots. Now, this one, for example, I added it. If you notice here, if you look in the left-hand side commands, the code, I added actually the text on the actual plot, and I put it right here in somewhere in the middle with this statement, simple statements, text statement that says, well, put the what I have in single quotes, which is label plots with the text command, and put it at the x-axis 5 and y-axis of 100, and that's in reference to your plot axis, right? So and again, in the previous statement, what I used, I had already defined x from 1 to 10 and y from 20 to 200. So that was already fixed. It wasn't changed when I plotted this again. But in this case, again, I'm using the markers, remember, and the colors associated with the marker. The O again just means the circle with the green color, or the other one for Y2, I'm using again a red color and an X marker, and for the next one, I'm using a blue with a solid line, right? And of course, I'm using the legend in this case, and I'm just labeling the legend with line 1, line 2, line 3. So this shows you exactly what happens, right? With the legend command, puts it on this corner. You can move it from that place if you want. The text command, same thing, right? You can place the text for your plots alone anywhere on the plot, and then the different colors for the different plots and different markers that I use in this case. Okay, one more example. Again, the only difference here is that we change the labels on the X and Y axis, and we added a title. Right, same plot as before, but this time we added a title with the X label for the axis. And we added a title or a name for the y-axis with this is the y-axis, and then the title, right? And one more thing we did is we adjusted the axis. We set them to show from x 0 to 11 and y from 0 to 200. So again, more control over what you can see. If you remember in the previous slide, we didn't have anything to control, the x or the y axis. So whatever was predefined already, whatever I was using on the previous plot, it kept those axes. On this one, however, as you can see, I changed axis from 0 to 11, so it's showing me the axis, x-axis, going from 0 to 11 because I decided to define it that way. All right, and one more thing you can do is you can use Greek letters in your titles or labels if you want to enhance those titles or labels with those Greek letters by just putting a backslash before the name of the letter. You can also create a superscript by using a caret, and you can create a subscript by using an underscore. If you have expressions, then the expression requires a group of characters as either a subscript or a super subscript. You will need to enclose them in curly braces. And to create a title with more than one line of text, you also going to need to use a cell array. And this is very simple. I'll show you the next example. So the plot here, as you can see, is just simply a plot of the power, instantaneous power that we've been using in several examples, right? And so we're plotting, again, as you can see, on the x-axis, we use T and P from a previous values that we obtained, which are not relevant in this case. We just want to show the plot and the different things that we've used or added to the plot. Of course, the legend I use is power, right? And I added a text box, if you will, which you can see right here. And given the location of the text, right, approximately knowing where the size of X and the size of Y, right? So kind of started at the middle of where X is, right? Because X goes from 0 to 1500, so I put it at 750, and I put at the Y of about minus 15, which bring it somewhere around here. And then, of course, like we said before, we can use Greek letters, and to use Greek letters, you use the forward slash. And in this case, I'm saying theta equals theta V minus theta I. And again, I'm using two of the things I mentioned in the previous slide. One is to use Greek letters, I'm using the forward slash, and to use the subscript, I'm using the underscore, as you can see right here. Okay. On the X label, you can see time, and in the Y label, you can see watts. And if you notice now, the title has 2 lines, right? And so in order for me to use more than one line, I'm going to separate the lines by a semicolon, but I want to put the lines in braces, in curly braces, as you can see here. So I have my first line is, so if you use just one line, you don't need the curly braces, right? This is only if you use multiple lines in this case. And each of the lines is defined or is going to be understood by using the semicolon here. So in this case, I have in the title instantaneous power, of course, in single quotes, right? Followed by the semicolon, which tells the plot to go to the next line. And then on the next line, I have, the definition of power in terms of voltage and current, in terms of voltage and in terms of current. And I ended up by curly braces so that the command understands that that's what the second line. I've also noticed that I've also used the caret here to show a super subscript, right? In this case, the square. Okay, and as you can see, this makes it look really nice, really presentable. Okay, another useful feature is the use of subplots, and with subplots, you can subdivide the window into a grid of n rows and n columns, meaning that you can put multiple plots on the same window, not necessarily on top of each other, but actually independent plots. So you basically subdividing the figure window into a matrix, an n by n matrix. The windows are numbered from left to right and top to bottom. Okay. The command that is used is the command subplot. And in this, using this command, we'll split the figure into an m by n matrix. And the variable P here will identify the portion of the window where the next plot is going to be drawn. So for example, in this statement here, subplot 221, the windows are divided into 2 rows and 2 columns. You can see this at the bottom here, right? Each of these windows will be a plot. So in this case, we have 2, 2, 1, again, meaning you have 2 rows, 2 columns, and the plot is drawn in the upper left-hand window. So if I'm using this command, the plot that I'm going to plot is going to be plotted on this window because of that's number 1. Okay. An example, I have this statements here, right? I'm defining the range of x from 0 to 2 pi in steps of pi over 20. And then I'm defining the subplot 2, 1, meaning that I'm going to have 2 rows and 1 column. So as you can see here, I have 2 plots, 1 on each row, right? And that's all. That's all I have in this case. And what it's saying is that, okay, the next time you plot something, plot it on the first window, which is this one here, according to our, definition, previous definition. So the next plot that is going to be plot is x sine of x, right? It's this one, and it's going to put it on top. And then I'm telling to MATLAB, well, the next plot, I already have it defined as 2 rows and 1 column, if you will. The next one plotted on location number 2, and the location number 2 will be the bottom here. And so it's going to plot x sine 2 times x on the second window. So again, this defines 2 windows, 2 rows and 1 column, with the top window, being indicated by this number 1, and the bottom window indicated by this number 2. All right, the next thing I want to show you is the uses of polar plots. We can generate polar plots by using this command, polar plot. And we enclose as an argument, we enclose the angle in radians and the radial distance of the value here. And it's very simple, and it can be useful to visualize numbers, especially when you deal with complex quantities. Maybe a nice feature to visualize it. So in this example, again, paying attention that I'm using some of the other features we talk about to make it look a little more readable. If you go to the title first before looking at the other details, the title says the sine function plotted in polar coordinates is a circle, right? So this is the polar plot of the sine function. So again, I've defined the values of x from 0 to pi in increments of pi over 100. And then I simply define y as the sine of x. So now I want to plot it as a polar plot. So as a polar plot, I need 2 arguments again. I need a theta argument, which is the the value in radians here, which I have defined as x, and y, which is just the actual plot that I want to show. So y again in this case is the sine of x, right? The sine of y, I'm sorry, sine of x, defined as y. And so by running this statement polar plot, it creates a function of polar coordinates that are defined by the sine function. Okay. Again, this could be useful for when you're plotting or when you're trying to visualize complex numbers. Another example, just to show you, some of the things that you can do. In this case, again, I've defined theta as going from 0 to pi and increments of 0.01 pi. And I define the function, or the radius, if you will, as 5 times cosine, and the argument is 4 times theta. And doing a polar plot like this creates this kind of, it's called the petal figure. And so, again, just to show you some of the features and things that you can do with MATLAB using the polar plot. Some of the other functions that we find very useful, obviously in engineering, is the logarithmic plots. And for those, we also have some built-in plots, functions rather. We have the semilog, the semilog x, semilog y, and the log function. The semilog x will give you a plot of the values of x and y, but it's going to use the log scale for x and the linear scale for y. This is typically what you will do when we do body plots, if you remember, for the magnitude of the body plot, where the x-axis is the log axis and the y-axis is linear. So using this command, semilog x, will give us that same feature. The semilog y is the opposite, if you will, of the x, because in this case, the x is linear and the y is the logarithmic scale. And the log, of course, is both being log, the logarithm scale for both x and y. Some examples here showing really, the three features or the three functions we talk about. We have a function y equals 5x squared, which is defined here in the statement. We have defined x as a variable from 0 to 50 in increments of a half. And we also making use of the subplot feature. And as you can see here, we have defined a subplot of 2 by 2. So we're going to have 2 rows, 2 columns. You can have more than that if you will. Although, you got to be careful, because if it gets too crowded, then you can't really see detail. I think, for visual purposes, 2 by 2 will be probably the most you can use. Maybe you can go 3 by 3, but who knows? Or maybe 2 by 3. But anyhow, going more than that, may be a little challenging to visualize. But you can use them. In any case, in this example, we have a 2 by 2, so we're going to have 4 plots. And it's telling it the command in MATLAB to put the next plot on the first location, which will be this one. So we're simply plotting x, y, right? This is just, again, the function 5x squared. So it's just plotting y equals 5x squared for those values of x. Okay. And of course, we're labeling y as y, and we're using the grid command so we can see the different distinctions in the plot, the different areas. The next plot says, okay, well, plot the next plot on the second location, which is this one, right? And I put in the title, this is a polynomial log linear function. And of course, the y label, the same thing. And it's just plotting this because I've used the semi-log x, right? It's just plotting this as a semi-log with x being on the log scale and y being on the linear scale. The next plot that's going to come in, I'm saying, okay, put the next plot on the third location here, and I want to see the semi-log, now y being the log on the log scale, and x being on the linear scale, and that's what you have. Okay, and of course the titles, again, I'm putting the title, this is the linear log example, and the labels again for each case. On the next one, the last one, which will be the fourth location because of the number 4 here, right? It's telling me to put that plot on the fourth location, and I'm telling it to plot or to perform the log function. So in this example, then both the X and the Y will be plotted in the log scale. And I'm putting the title here for that, okay? And with the labels. So as you can see, this will be, you know, very nice, and it includes the information that we want with the titles, information on the X and Y axis. You know, if we want something more detailed, we can put it like that, but you can see how nice this looks, right? Some other functions, commands that we can use to create plots. We have the bar, the different pi functions, and the histogram function. And the bar function, as that indicates, it simply generates a bar, right? Whether it's horizontal, whether it's vertical, whether we generating three-dimensional bars, like on this one here, bar 3x generates a three-dimensional bar charts. And the pi, of course, you know, generate a pie chart. If we're using, if you want to see a three-dimensional pie chart, we use this one. And then we have the histogram to generate a histogram. Okay. Examples here where you can see I've generated a vector with numbers 1, 2, 5, 4, and 8. And I defined then y as also another vector with the elements of x, right? And then I added another row from 1 to 5, okay, to, you know, to show the y-axis numbers, if you will. And if you use, again, using the subplot command, divided the area into 4 plots, 2 by 2 again. And I'm saying, okay, the next plot that's coming, put it in location 1, and that will be simply called the bar function. And all the bar function does is just to plot the values for x, right? So I have, you know, if you notice here, x is 1, x is 2, x is 5, you know, the value here, right? X is 4, and then the last one, x is 8, right? And that's just what the bar function does, a bar graph of vector x. The next plot on location 2 is a bar y, right? So y now has 2 rows, right? One which is equal to x, you notice this one here, and then it does the y1, which goes from 1 to 5, right? You can see that here, okay? And so you can create multiple bars in a single location, if you will. The next one is in location 3, which is this one, and it's the same information that I have on y, but just in a three-dimensional way, right? You can see that here, right? This is, you know, the information for 1 along this way, and this is the information for 2 along that way in a three-dimensional plane. And the last one is a pie chart of x, and I put it again in location 4, and simply call the function pi with the elements or the argument x, which includes the elements 1, 2, 5, 4, and 8. And you can see this, you know, associated with each of the numbers that I have. Okay. All right. Another example here. This time using a histogram, and I've created a vector of numbers associated with x, as you can see here. And the histogram would just tell me, you know, how many of those numbers repeat, or, you know, for example, you know, for example, I have numbers from 60 to 90, right? From 60 to 90, I have 8 numbers. You can count them. And from 0 to 20, I only have 1. So let's see, from 0 to 20, 22, that's it. 22 is the only one. So that, you know, tells me the occurrence of a number or the occurrence of an event. So from 30 to 60, I have 2 and so forth. So that's what the information that the histogram will tell you associated with this data. I didn't put any titles or anything here just to keep it simple, but again, you can always enhance it, change the colors if you will. You know, in this example, for instance, we changed the histogram and just to change the width, the how many bars I want to see. The previous one was done automatically. The program decided how many bins to create, how many bars. Each bar is called a bin, but I can also define how many of those bins I want. So if I change, this statement here in the Y box is what I had before, right? So that same statement generated this. If I want to just show 3 bins, I will change this statement histogram X to histogram X comma 3, and it'll divide it into 3. Okay. And again, that shows you, the same data, but visually differently. Because now you can say, well, from 20 to 50, I have 2 numbers, right? And you can corroborate that. From 20 to 50, 22, 34, and that's it. Right? 22 and 34 are the only 2 between 20 and 50. So that gives you maybe something that is better defined for the information that you want to present. In this case, because it's every, falls right on the 10, 50, 80, 110, and so forth. But it all depends on the data you have or how you want to show it. All right. Another useful feature is the use of y-axis. Remember I told you at the beginning how MATLAB every now and then retires functions or commands or replacing them by something that is improved and already had the previous feature that that is just repetitive, and it gets rid of whatever is repetitive in the upcoming versions. So the reason I mentioned this is because this function yyx, what it basically does is allows you to create a graph with 2 y-axes, one on the left and one on the right. You can see here in this figure, right? We have one axis on the left and one axis on the right, which could be useful if you want to show something back to back like this. And what I was saying before is that this y-axis function is going to replace the plot yy function. You may have seen that plot yy function, especially I think your book still uses plot yy, and it's still being used. But eventually it's going to be replaced completely. But either one of those 2 can be used to create that effect of having an axis on the left and an axis on the right. But get used to using y-axis because it's just a newer one. Again, a very simple 2 functions. Defining x from 0 to pi in increments of pi over 20. And 2 functions, y1 is the sine of x, and y2 is the exponential of x, as you can see here. And I've defined the plots into 2 areas, this time as columns, you can see, right? Because if you notice here, I really have one row, if you will, of plots, but I have 2 columns, right? I define in order to use the y-axis, I'm gonna tell it where to go. So y-axis left tells the command to to put the axis on the left, and then I say, well, plot x y1. So y1 is this, and I'm labeling the function which is not which is shown right here, right, for the y-axis. Sine function, and it puts that the axis on the left. Okay. For the next plot, which again I'm putting on the second location, which is this sort of orange line here. Again, I'm defining the y axis to the right. I'm saying, okay, this axis now is going to fall on the right-hand side. And I'm saying plot xy2, which is the exponential function, and is labeling that y-axis as exponential function. Okay? All right. Notice that I didn't put an x-axis on the second one, but just, you know, it should be an x-axis here, but I didn't put the label in it. Is missing, and I guess it's a good thing to show you what happens if I didn't do it, right? Because you have to do it for every plot. Every little plot that you're having here, you have to redefine the axis, so or relabel it, if you will. All right. Another example with a graph with two axes, and this time on the same plot. Notice that I simply basically have the same commands that I had before, right? The only thing I did was to comment out the statements that define the subplot. So in this case, since I'm using the hold on command, it's just going to plot one figure on top of the other one. I mean, that's it, right? Very, very simple. The only difference here from the other things we have been doing is that now we have two axes on the y-axis, right? One on the left, one on the right, and one associated with the exponential function and one associated with the sine function, which is very nice, right? All right. Okay, so now we look at another function, the f-plot function. These are under the label of function plots. And the f-plot function allows you to plot a function without you having to define an array for the x or the y values. MATLAB will automatically calculate the spacing of the x values and will give you a curve. And this is for something that if you want to just kind of see how it looks like, and you're not really concerned about defining the axis, but just want to see how it looks like, maybe a behavior, is a very nice function to use in that case. The first argument in the f-plot function starts with the add command, okay, or the add symbol, rather, I should say, to specify the independent variable, and then continues with the function that's going to be plotted. The second argument is an array that's going to define the range of the plot. For more complicated functions that may be inconvenient to enter in this way, then you may want to use the anonymous function and instead enter the function handle or the function name as we did previously. So this is for something that is not really complicated, but again, you may just want to see how it looks like. Function plots do not require you to define arrays of order pairs, like I said at the beginning. So as you can see here, if you follow the formatting of the plot, of how you use f-plot, we have the first argument starts with the add symbol, okay, and specifies the independent variable, and then it continues with the function that you want to plot and the range, okay, what range you want to see. So this is the plot of x versus sine of x for values of x between minus 2 pi and 2 pi. Okay. And the result of that is this, as you can see. It's not going to change how how the plot looks like. You're still going to have to, do things to make it look the way you want it to look. I didn't do that in here because I just want to show you quickly how the f-plot command works. And again, in this case, x is the independent variable. Sine of x is the function you want to plot, and this in brackets is the range, the plotting range. So it's a very quick way of setting up a function, if you will, right? And again, notice that the thing here is that we didn't really worry about uh, defining specific values for the variables here. The function itself decided, how to plot it. Okay. Other functions. This is getting into the realm of three-dimensional plots, and sometimes, a lot of times, it's really useful to look at the plots in 3 dimensions. It gives you a lot more information, obviously, as you know. And so we have several functions in MATLAB that are really, really powerful to create 3-dimensional plots. Really, really nice things that you can do with 3-dimensional plots in MATLAB. And so we have different functions here built in. We have the plot3 function, which creates a 3-dimensional line plot. The Comet3 function is really just cool to see. We're not going to do it here in this lecture, but you may just want to try one time and see what it does. It just basically creates a plot, but it's doing it in an animated way. It's just showing you slowly how the function is being built. Sort of an animation way of looking at the plot. 3. The mesh function, which creates a mesh surface plot. We have the surf, which creates a surface plot, and some other things that we can do with it, and we'll see in the next couple of slides here. For example, the plot3 function is similar to the plot function, except that now you have 3 dimensions, data in 3 dimensions, not just 2 dimensions. Instead of just providing x and y vectors, we also have to give it another z vector, if you will. Okay. So in this example, for instance, I used the linspace command to create 1,000 points from 0 to 10 times pi, okay, for the x-axis. And then the y-axis is going to be the cosine of x. And the z-axis is going to be the sine of x. And of course, the z-axis is pointing, up, right, in this direction. So if I use the plot3 command with x, y, and z as the arguments, and I'm putting a grid here so you can see the more detail. I'm labeling the x label, the angle label, the angle axis, the y label, the cosine axis. Right here, cosine axis, sorry, x, y, and the z label, the sine axis, right? So, and the title, just the spring, right? Because it simulates a spring, if you will. So, and again, just this plot here, right? This plot3 command takes on the values of x, the values of y, and the values of z to generate this function. Okay. All right. So obviously, as you can see, if you were to just look at the x-axis I'm sorry, the y-axis, which in this case is the cosine. If you were to look into that direction, you will see a cosine wave. If you were to see into this direction along the angle axis, you will see a sine wave, right? But if you went to see into the into the y-axis, then you see the 3-dimensional figure. Okay. The other useful commands in MATLAB is the surface plots, and I put this figure here because that's the way you generate this kind of function, right? If the more cooler type functions that are really, shows you a lot of information, are a lot of them being built with this type of commands, like the surface or the mesh commands that we're going to use to generate that kind of plot. So the surface plots allows you to represent that data as a surface. Well, we're using 2 types of surface plots. One is called the mesh and the other one's called the surf. The mesh takes on 3 variables, in this case, X, Y, Z, and creates a mesh plot, which is basically just a 3-dimensional surface that has solid colors and no phase colors. The function plots the values in the matrix Z as heights above a grid in the XY plane defined by X and Y. In other words, you have, X, your typical X, Y, and then the function mesh just plot the values along the Y-axis, right, in that direction. The edge colors may vary according to the height specified by Z, which is also useful, right, visually to tell you. If you were to look at this function, for instance, at this plot from the very top, like a helicopter view, you wouldn't see the heights, right? You would just see the colors as a flat surface. So it's a way for the information to tell you the different heights by looking at the color. So if you look at this from a bird's eye view, if you will, then you will see at the center, you will see red. And then next to the center, you're going to start to see yellows. And then, going further away from the center, you may want to start seeing green. And then going towards the edges, you're just going to see blue, right? So that's why we're saying here that the edge colors will define the heights, right? Mesh C, on the other hand, creates a mesh plot and uses the column and row of the indices of the elements in Z as the X and Y coordinates. You'll see the difference in just a minute. And in this case, if I use mesh Z and C, I can then specify the colors that I want to see along the edges. Okay. So let's look at some examples of this. In this case, I have a variable Z, right, with 3 rows. And if you look at the case of mesh Z, right, I'm using one variable Z, and that variable contains columns and rows, right? And it's going to take it as the X and Y coordinates. So as you can see here, in this direction, I go from, up to 10, and then on this direction, I go up to 20, and then you can see, in this case, MATLAB is deciding the best way to, since I'm not saying anything else, just to plot it as a mesh. I'm not defining any of the axes that I want to see, but MATLAB automatically decides that to give you the better view, if you will. So that statement here, mesh, simply just created a single 2-dimensional mesh of a two-dimensional matrix. That's all. All right. The mesh function can also be used with 3 arguments. Remember in the previous one, I used 1 argument. If I use 3 arguments, in this case, X is the list of the X coordinates, Y is the list of the Y coordinates, and C obviously is the list of the Z coordinates. The X vector must have the same number of elements as the number of columns in the Z vector. That's the only one thing you got to remember. And the Y vector must have the same number of elements as the number of rows in the Z vector. Okay, so we have to match that. So in this case, as you can see, I've created I use the linspace command to define the x-axis, right? From 10 elements from 1 to 50, right? And in the case of y, I have defined this from 500 to 1,000, and I'm using the three argument specification here. Now it didn't change the shape basically, and it shouldn't change it. As you can see, it's still the same. But what it does is, if I use the three argument command and have more control over what I can see along the axis. See here, right? Previously, if I don't use the three variable command, then MATLAB will decide how to show it. But using, defining the X and the Y, kind of, it gives me a little more space. I think it looks a little better that way, but you can define it, It's not going to change the shape, like I said, but it changes how much of the information you see along the axis. Another example, on this one, I have generated a random variable just to show you. This time it's just another random set of numbers. And again, the Z matrix is used to index numbers for the X and the Y axis. In this case, my Z matrix is A, if you will, right? And I just let MATLAB decide, how to plot those, how to generate the plot. But in essence, again, what we have is just a matrix of numbers here, right? And is a 3x10 matrix, and using mesh to plot that function in 3 dimensions. Okay. Another example, in this case, again, showing you how you can also, adjust the function. You can adjust the colors, you can adjust the width of the lines, you can put titles and so forth on the XY axis, and do some of the other things you do with the regular plots. Okay. In this case, again, we have a mesh like before, but this time we define the width of the lines as 2, so it's thicker than before. We put a title and we label the axis. X label, X axis, Y axis, Z axis. Just like we did with the regular 2-dimensional plots, but again, just to show you that you can use the same commands to label your plots any way you want. You can put a label like before, put multiple titles, and so forth. The surf plot, which is the other one that is very useful, are similar to the mesh plot, but the surf creates a 3-dimensional color surface instead of a mesh, right? A mesh, like the name describes, is just a mesh, right? It's like a metal fence, of the different elements. Surf basically does the same thing, but it's just going to put colors on each of the surfaces. Okay, so by using surf, you create a 3-dimensional color surface instead of the mesh, and the colors vary with the values of Z, right? You can control what the colors associate with the numbers by using putting on inside these commands, and we'll look at that later. But if you don't, then MATLAB will decide what colors to associate with the different areas here. So the surf command takes the same input as the mesh, either a single input, for example, surf Z rather, in which case it uses the row and the column indices as X and Y coordinates, or uses a three-dimensional matrix like the ones we used before. And either way, the result is the same as in mesh, except that now you have colors. In this case, this is the same numbers I use for the mesh representation, or the mesh example I gave you. And as you can see, the axes here are not are controlled by MATLAB, right? I didn't define it. But on this one, using the same values that I used before here, right? I'm sorry, same command that I used before for X, Y, and Z. This is this one here. Sorry, this one, right? I define, just like before, see, I define the the spacing for X and the spacing for Y axis, right? The only difference, so that's still the same. X is still the same. Y is still the same. Z is still the same. Matrix of numbers. The only thing I change here is the surf. And that's the difference now, that the surf will give me color. It's going to shade the different cells and give me colors associated with each of the cells. And again, using the three-dimensional or the three argument command will allow me to define how much do I see along each of the axes, which again might be something useful. So the curves are the same. It's just, you know, the look is going to be different. All right. The other thing you can do is associate a color with you know, with the plot, the colors that you want to see. And for that, you can use this color map function. It controls the colors that you're going to see in the surface plots like this, right? And I'm not going to go into that detail because that's a little, you know, you really, it's a little too much detail, I think, at that point, right? If you want to decide what colors to use. So I'm just gonna let you look at the help command here under color map and see, it's gonna show you the list of colors, okay, that you can apply. So if I use that as an argument also for this surf plot, after that, I use the color map and define a color set that I want, then I'm gonna see different colors here, that's all. All right. The other thing I want to talk about is, remember a couple of lectures ago, we mentioned mesh grid. And we use mesh grid to create rectangular structures from a given array, which is useful to representing indexing in a matrix. And the way mesh grid is used, and the reason I'm bringing it here is because it becomes useful when you're plotting something, and understanding, you know, how the plots are created. So the way you use it is you call the mesh grid command with two variables, X and Y. And by calling it, it returns a two-dimensional grid coordinates, in this case for capital X, capital Y, based on the coordinates contained in these two vectors. And then X will be a matrix where each row is a copy of X, and Y is a matrix which is column is a copy of Y. And the grid represented by the coordinates X and Y is going to have a length of Y rows and a length of X columns. And what that does is it allows you to create a grid of numbers, because when you plot, if you try to plot a two-dimensional plot, or rather I should say, if you try to plot a two-dimensional function using a one-dimensional plot, it's not going to give you the whole information, right? If you try to plot a three-dimensional plot using regular plotting information, you're not going to see everything that you want to see. So for example, if you want to plot x squared plus y squared, right, as a single two-dimensional plot, you can only see one piece of information at one time in 2 dimensions. But if you want to see a three-dimensional plot, you know, if we want something more along these lines, right, which is a more complicated surface, then you'll need to use the mesh grid command so that the plot can understand where to put those values, okay? So in this case, we created a more complicated surface by calculating the values of z. Again, we define x as going from -2 to 2, and y is going from -2 to 2, and increments of 0.2 for each case. And we then use the mesh grid to create a mesh from these coordinates so that the plot is going to use these new generated matrices, capital X, capital Y, to understand where to put the individual coordinates here for the plot. In this case, we're recreating a function x times the exponential of x squared minus y squared. And we're using two plots. We're using 2 rows, 1 column. And we have, when we tell the MATLAB to put the first plot on the top, and it's just a mesh of the z function here, right? That's what we label it, or we title it mesh plot. And of course, we labeling the z-axis, the y-axis, and the x-axis, as you can see, along with the title. And then on the second plot, we tell it to go into the second location. And this time we're using the surf command for the same plot. As you can see, is it identical? We're using the same labels, different title, obviously. But the difference is that now, if you use mesh, you see, the idea of a mesh. And if you use a surface plot, it shades the different cells with different colors. And again, you can define how these colors may look like by using the color map command. All right, and I think we're going to stop at this point, and we'll continue next time. Email me or set up an appointment with me through Zoom if you have any questions. I'll be happy to talk to you. Thank you.